up next. Hang on just a second. Let me zoom out while I work on a technical problem for 1 second. I think it's fine. Okay, so on to the next problem I've got prepared. We're looking for a decomposition of the vector A into two other vectors. We want to break it down into a component that is parallel and perpendicular to some other vector B. So again, we're going to call that a decomposition into parallel and perpendicular components, or parallel and perpendicular parts. So this is similar to the way that we would take a vector and break it down into its x, y, and z components. That would be decompositioning it into its x, y, and z components. But we can also decompose any vector into elements that would be parallel and perpendicular to whatever vector system we want. This particular case, we want to look in the B direction and then figure out which parts of A run parallel to B and which parts of A run orthogonal or perpendicular to B. So I've got a diagram that I thought would be helpful to sort of discuss what it is we're actually trying to do. If we've got the blue vector, which is A, that is the one that we're looking to find a decomposition of. I want to break it down into its pieces that run parallel to some other vector, which is going to be B, the one that's in gray. I want a component that's parallel to B, and then I want a component that's perpendicular to B. So that parallel component is just going to be only the part of A that runs parallel to B. That's denoted by C, which is in yellow. That's going to be the first thing that we find. And then after we found the parallel component, we'll use that in order to find the perpendicular component, which is that bit D that's denoted in magenta in the diagram. So, for starters, finding the parallel component means that we want to project A onto B. That's going to be our first goal here, projecting A onto B. So really, I just want the part of A that runs in B's direction. We have an equation for that, and that projection of A onto B is going to be the dot product of A and B divided by the magnitude of B, and then we're going to multiply that into the unit vector in the B direction. So if we think about the two components of that projection that we have going on, the second component, which is this piece right there, vector B divided by its own magnitude, that's the unit vector in the B direction. All that piece is telling us is that this is the direction we're interested in going, but it has a magnitude of 1, meaning it's got an ignorable magnitude. So the magnitude of that unit vector doesn't impact the actual projection of A. Just tells us which direction we're going in. The other part then, the dot product of A and B, then divided by the magnitude of B, is what's going to give us the component or the length of A that goes in B's direction. So that's just going to be the scalar length of A that goes in that B direction, which if we're looking at that dot product, it's A and B roughly being multiplied together, and then we're going to divide away the magnitude of B. Right, so we're getting rid of the B magnitude, which means we should only be left over with some component of A that is tied to B, but not necessarily B's magnitude. So that's our projection. But at this point, all we really need to do is plug some stuff in to get an answer. We'll take a magnitude and multiply it into a unit vector. So let's take a look at what that's going to be. I'm going to need more space than that. Let's start it on this end. So my first numerator, I've got a dot b, where a is the vector -3, 5, -5. Comes from that line up there. I want the dot product of that with the vector 1, 10, -2. Try that again in a 1, 10, -2. There we go, that'll show up a little better. And we're going to divide that thing by, I need the magnitude of b, but I need it twice, once for each part of those two fractions are multiplying together. So I'm just going to combine those together to just calculate the magnitude of b once. So the magnitude of that vector should be 1 squared plus 10 squared plus 2 squared. And then we're just going to square that square root. Because again, we're multiplying the magnitude of b into itself. And then we're going to multiply this value right here, which at the moment is going to come out to just a scalar value. This is just a single number. Number on screen is not a vector anymore because the dot product gets us to a scalar value rather than a vector value. Our denominator is already just a number. So everything on screen right now is just a number. We want to multiply that into a vector. And the vector we want to multiply it into is the direction we want to be going, which is b. So 1, 10, -2. Then we just need to simplify that mess a bit. Let's see, up top, we're going to get -3 plus 50 plus 10 divided by the bottom. Well, I've got the square root squared, so I don't need to worry about that anymore. I've got 1 plus 100 plus 4. Again, being dotted into the vector 1, 10, -2. And then finally, just clean up that fraction a little bit. This is 57 divided by 105 being multiplied into the vector 1, 10, -2. And for simplicity's sake, I'm going to leave that as it is. I don't really think there's a particular need to multiply that 57 over 105 into each number. Nothing's going to simplify if I do, so I'll just leave it right here. Some scalar value times the vector b, which is what we know we ultimately want to get here. We're looking for the projection of a onto b, which means our vector should go in b's direction. It is just a matter of some scalar multiple of b. Right. So that's C. That was our parallel component. Now, to get to the other half, because we wanted to decompose this vector A into both a parallel and a perpendicular component, so we still need to get our perpendicular component D. But it's helpful to notice here that if we're decomposing A into its parallel and perpendicular components, that means that if we added those two components together, we would get back to A, right? If we look back at the diagram, it doesn't matter if so there are two paths that lead us both to the endpoint of vector A. We either traverse along the blue line, which gets us to the endpoint of A, or we could traverse along the other two components, first the yellow and then the pink component, which also gets us to the end of A, which means that those two paths are equivalent to each other. So the vector A is just equal to the sum of the C and D vectors together. Meaning that if we wanted to get just D, that magenta vector, I could take the difference between A and C, the difference between the blue and the yellow vectors. So to calculate that perpendicular component, I'm just going to take A and subtract C. And we have all of that already. A is the vector -3, 5, -5. And C is the vector 57 divided by 105 times 1, 10, -2. Just to emphasize that this is still B, I'll put it back in B's color. Cool, so those are our two components. Again, I'm gonna leave it as is rather than trying to combine those pieces. It's not gonna go to a particularly nice looking value. So I think it's a bit more readable if we leave it in this form. Right, next up, what are we after? Suppose the magnitude of A is 4 and the magnitude of B is 2, and the angle between A and B is pi/3. Find the value, magnitude of A cross B. So we're calculating a magnitude here, meaning that our solution should be just a scalar value, so just a number. Scalars are just numbers as opposed to vectors, which are a collection of 2 or 3 values put together in one string. As long as we're working in either 2 or 3 space, which is mostly what our course will be concerned with. So again, we want the magnitude, which is a scalar value. So we're just looking for a number this time. Normally, if we wanted to get the cross product, we would line up our two vectors and do the fancy cross multiplication stuff. But if all we need is the magnitude, there's a secondary definition that we can use to just get the magnitude out of the cross product without actually needing to know the specific values of those two vectors. So one of those things that we have, the magnitude of A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle that's in between them. And we know each of those three pieces. We know that the magnitude of A is 4. We know that the magnitude of B is 2. And we know that the angle between them is pi/3. And as long as we're not specifying degrees, you should assume that the angle is given in radians. And in particular, pi/3 is a pretty common radian angle measure. So 4 times 2 times the sine of pi/3, that looks like 8 times the square root of 3/2, if you remember your values from the unit circle. And we can simplify that a little. Call it 4 times square root 3. All right, speaking of the cross product, let's actually calculate one. So our goal in the next problem, we're given a collection of 3 points, which will denote some triangle. And we want to find the area of that triangle. So if we look to the diagram over on the right, I've got one drawn out over there, depicting the area that we're attempting to calculate, that triangle that is denoted by points A, B, and C. And I'm also drawing on the implied parallelogram that goes along with that triangle. Since we know from another one of our definitions that the magnitude of the cross product is equal to the area of the parallelogram, denoted by, that is, constructed by the two vectors that we're crossing. And it so happens that if we cut a parallelogram in half, we'll get exactly the triangle that we're after. Triangle with these three points. So what I might want to do is look at vectors AB and AC. Start writing that down. I want to get vector AB, and I want to get vector AC. A vector AB and vector AC. And then take the cross product of those two vectors, which will give me the area of the parallelogram. And then once I've got that parallelogram area, I can just cut that in half to get the area of the triangle. We often see a 1/2 show up when we're calculating areas of triangles. Works the same way with this method. So without further ado, let's figure out what these vectors are. Also, I suppose it's worth noting that as long as we have a triangle, it won't matter which two vectors we decide to take. We could do AB, AC, or even BC. Any two of those three vectors crossed together will give us the same magnitude. So keeping that in mind, we chose to connect A to both B and C, but that wasn't the only step that we could have taken. Could have connected any one of the 3 points to the other two. Right. Let's have at it. Like I said, without further ado, and then I had a lot more ado. Should see to that. Okay, the vector AB. Starting at B and subtracting away A, I'll get -6 minus -3. Then I'll have 3 minus 1. And then I'll have -2 minus -2. Oops, put a comma where I did not need one. -2 minus -2. Scoot this down a little bit so I don't run into my picture. That's going to give me the vector -3, 2, 0. If we go at that again, but this time connecting A and C. So I'll start at C and subtract away A. Means I've got -5 minus -3. And then I'll have 1 minus 1 and -2 minus -2, giving me the new vector -2, 0, 0. So those are the two vectors that I then want to take a cross product of. So let's get that cross product. I want the vector AB cross the vector AC. And it looks like I J, K. -3, 2, 0 goes right there. -2, 0, 0 will go there. And let's come together to find a vector here. So with that k column being equal to 0, that makes our cross product particularly easy. Any cross multiplication step that involves the third column is going to come out to 0 since both numbers get multiplied by 0. So the only one that will be non-zero will be the one where we're expanding without k. So the one that is in that third position. So the I component is going to be 0. The j component will be 0. And then the k component, -3 times 0 is 0. -2 times -2 becomes +4. Maybe actually write that out a bit better. -3 times 0 minus 2 times -2. 0, 0, 4. That's our cross product. So in the end, we just need to get to the area, which is 1/2 of the magnitude of AB cross AC, which is 1/2 of the square root of 0 plus 0 plus 4 squared. And then square root of 4 squared is 4. Half of 4 is 2. So our triangle has an area of 2. Zoom in a bit on this one. Up next, we want a non-zero vector normal to the plane given by that equation. So, nice thing about the equation of a plane, well, first, all 3 of our terms are going to be linear in a plane. So x, y, and z all have a power of 1. Any equation like that in 3 space is going to denote some kind of a plane, as long as all our terms are linear. So we've got that already. And if we arrange the equation of our plane in standard form, we'll have a normal vector that just shows up nicely for us. So let's put this equation into standard form, which means we're just going to multiply all our numbers out. Or I guess that's actually general form, not standard form. There is a difference. I think it might actually, it's already pretty close to what standard form would be. But again, we want general form. So multiply our numbers through. We're going to get -5x plus 15 equals -16 plus 4y. And then I'm going to bring everything over onto one side. And I'll also arrange it so that x is first, then y, then z. So bringing everything to the left side, -5x minus 4y plus z plus 31 is equal to 0. Let's keep our equal sign in the same spot. And then the normal vector for this plane, or at least a normal vector for this plane, shows up in the coefficients to x, y, and z. So that normal vector, or at least the easiest normal vector to pick out, is going to be -5, -4, 1. Normal vector we're into. -5, -4, and +1. So that is the easiest non-zero normal vector to pick out for our plane. We'll just get it into general form, which means we put all of our terms on one side, expand them all the way out. Doing that, we just need to pick out the coefficients on each of x, y, and z, and that's our normal vector. Beats having to calculate it some other more complex way. But speaking of more complex calculations, our next problem. Zoom out a little bit so I can have the picture that I drew on here. So our goal in this next problem, we're going to find the distance between a plane and a line. So we talked for a moment about what that should look like. We've calculated the distance between a point and a plane before, and that's gone relatively okay. There's a formula that we have for that. Distance between a point and a plane makes a lot of sense. We just take our point, find the shortest distance to the plane, and calculate our distance that way. Now, calculating the distance between a line and a plane is a bit more of an interesting question, since there would be an infinite number of points that we could choose on that line. And some of those might be a different distance away from the plane than others. So it's worth considering the two types of organizations for lines and planes that we could have. So most of the time, pick a random plane and a random line in 3 space, and they are going to intersect somewhere. If that's the case, if we have an intersecting line and a plane, well, if they intersect, the distance between them should be 0. We just find the point of intersection and say, hey, these two things intersect somewhere, so the distance between them is 0. And that's sort of the case that we wouldn't really consider in this kind of a question, because the other option would be that we have a line and a plane that do not intersect. And the only way that's going to happen is if our line and our plane are parallel to each other. So it's just like when you have two parallel lines, or if you have two lines that never intersect, they have to be parallel to each other. Same with a line and a plane in 3 space. If they never intersect, they must be parallel to each other. And if our line and our plane are parallel to each other, that means that the distance is going to be the same no matter where I am on that line. Because again, it's got to be parallel. So the distance should be the same everywhere, which means we don't need to check multiple points. We can just find a single point on our line and look at the distance between that point and the plane. So really, if we're looking to get the distance between a plane and a line, it is the same as finding the distance between a point and a plane. We just have to pick some point that's on our line. So, with all that said, let's do that. So, I'm going to pick out some point that's on our line, and I'm just going to give it a name. I'm going to call it Q. Q is going to be this point up here. Some point on the line, I'm going to look at finding the distance from point Q to our plane. Which means that if I'm calculating the distance between a plane and a point, I also need any point that is on the plane. So I'm going to pick that too. How about we call it point P? Cool. So I'll have a point P and a point Q. I can look at the distance. Let's ignore that for a second. Let's start by just connecting those 2 points, P and Q. I need a new color. Looks like blue is roughly what these two have in common. I don't want to use red. Cool. So I'll look at this vector right here, PQ, If it's a vector, it should have a direction, so it's going that way. Cool, so I'm going to connect the point on our plane to the point that's on our line, and then say that that particular vector right there isn't exactly optimized. That's not going to be the shortest distance between the line and the plane. But since I've got a normal vector on our plane, I should be able to use the shortest distance to connect those two guys together. So I'm going to look at extending this normal direction out of our plane P. I know that the shortest path will be along that direction. And let's call that new distance C, or that new vector C. So by our construction, that vector C is going to be the shortest distance to get from the plane up to the line. And if we look at the way that we constructed that vector that connected our 2 points, P and Q, what I'd really like to do here is project our vector P onto that normal vector direction. If I look at the projection of PQ onto the normal vector, it should give me C, which is the thing that we're going to want to have. So what that then requires is finding those 2 points, P and Q, as well as a normal vector for our plane. So we've got a thought process here. So let's put it together. If we look at our line, and it looks like it's a parametric equation, but the line, I just need any point that is on that line. Let's go with Q. For example, t equals 0 is a pretty easy point to calculate. So why don't we get that? So if we take the point t equals 0, then our point on Q could be -1, -2, -1. Which is also the same point that shows up in the equation of the line. -1, -2, -1. Now, my choice here for this point is completely arbitrary. I just need any point that is on the line. I happen to choose this one, but I could have chosen any other point that's on the line and this would still work. So like I said, t equals 0 is just the easiest one because it required the least amount of calculation to get there. But take any other point on the line and this process will still work. My choice here, again, is arbitrary. Didn't have a particular rhyme or reason for picking this point, aside from the fact that it was going to be easy to calculate. So up next, I need a point that's on the plane, which I come up and take a look at the equation of our plane up here. I've got x plus 3y plus 2z equals -23. And again, any point will do. If I'm again going to go with the point that requires me to do the least amount of work or the least amount of calculation, then x equals -23 and y and z are both 0. That'll fit on that plane. -23, 0, 0. And again, I got that. By looking at my equation, x has a coefficient of 1, so that's a pretty easy value to solve for. And I get free choices here that I can make, because again, I need any point that's on the plane. So I'm just going to elect to have y and z both be equal to 0. And that leaves -23 for x. Again, a completely arbitrary choice for this point. I just needed anything that's on the plane. This happens to be one of those points. Then what else do we need? We're going to want that normal vector. So let's maybe come over here to the left side and write that down. Our normal vector is going to be 1, 3, 2. Where again, I'm grabbing that from the equation of the plane. So how about I highlight that with some green? That 1, 3, 2, those are just the coefficients on x, y, and z in the equation of the plane. So numerically, those are all the values that I'm going to need in order to get this distance. So now I'm ready to start calculating some stuff. Moved on to where I've got some work or some space for work, but also still have everything on the screen. Right here looks good. So I want to find, what is it? I want to find the vector PQ. That's what I needed first. I picked my 2 points. Now I just have to find the vector that connects them. So PQ is well, I'm going to start at Q, and then I'm going to subtract P. So I need -1, -2, -1, minus -23, 0, 0. I should just write that all out. This looks like, again, I'm starting at Q. So -1 minus -23. Up next, I've got -2 minus 0. And then I've got -1 minus 0. All together, 22, -2, -1. Then, the part that I wanted is the magnitude of that yellow vector that I drew in. The actual distance I'm trying to get here. Magnitude C. If I plug that stuff in, let's see what we get. What's it come out to? I need the dot product, or okay, right. C is just the component of P cubed, the component of that blue vector that's in the normal direction. So let's look at the component of PQ that goes in the n direction, which we know is the dot product of our 2 vectors divided by the magnitude of the direction we want to be going in. So I want the dot product of 22, -2, -1, and that normal vector 1, 3, 2. It doesn't show up that well if I write that 1, 3, 2 divided by the magnitude of that direction vector. So 1 squared plus 3 squared plus 2 squared. Oh. And we can get a collection of numbers there. Across the top, 22 times 1 is 22. -2 times 3 is -6. -1 times 2 is -2. Divided by the square root of 1 plus 9 plus 4 is 14. So this looks like 14 divided by the square root of 14. And if we rationalize that or simplify it, we get just the square root of 14. So that's got to be the distance between our point and our line. And that's the explanation that I tend to think makes the most sense. We actually do have another option here. And that is to use a simplified version of that distance formula, but I think some of the understanding of why this distance formula makes sense gets lost if we use the other equation, but it can be a bit faster. So we might as well talk about it in the exam review section. So an alternative method for calculating that magnitude. I should put a big like or right here. We can use the other version of the distance formula, which looks like this: 1 times -1 plus 3 times -2 plus 2 times -1 plus 23. All of that over the same magnitude that we would have just calculated. Okay, come back. That's 1 squared plus 3 squared plus 2 squared. And if we do that whole mess, we're going to get the absolute value of -1 -6 -2 plus 23 divided by, divided by the square root of 14, which will again be 14 over root 14, which simplifies to root 14. So talking about this second equation that we just used, if we get the equation of our plane into general form, which means we move everything over to one side and then have it equal to 0, we can plug in. We can then plug in any point that is on the line into that plane equation, take its absolute value, and then divide it by the magnitude of the normal vector. The work, as you can see, I think is a bit simpler, right? We didn't end up needing to pick a point that was on the plane in order to calculate that value. But the downside to this second option is that I really don't think you quite get the full picture of what's happening if you just rely on that formula. Also, I noticed that formula tends to have a lot of mistakes in it when it tries to be applied. So personally, I prefer the top equation, even though it's slightly more work, which is rare for me. I usually like whatever the easiest option is. But I like that first method because it actually involves some amount of conceptual understanding of what's happening, as opposed to the formula on the bottom, which it's faster, but I know that I always struggle remembering what that formula is. Whereas if I think about it as a projection, I usually do a better job of arriving at the correct answer. Right, lines and planes. Let me grab the example from the notes that I'm referring to here. Come find our spot in the review and post that in. Paste that in. Post it in, paste it in. Okay. So here's that spot from the notes that I was just referring to. The one that has our new formula, that distance formula there, d, maybe shrunk it down a little bit too much. Come on, I believe that you are capable of resizing here. Maybe. There it goes. Okay, so that distance d again, we can take what's very close to the equation of our plane. But again, it's got to be in a specific form. It must be in general form first, which means everything's over on one side and then it's equal to 0. Oftentimes we like writing it equal to d, but d actually needs to come over to the other side. So the most common mistake I see when people are trying to use this formula to get the distance is that lowercase d that shows up on the inside of the formula, this guy right here, that guy tends to have the wrong sign frequently. And we don't want that. So yeah. Just note that if you are going to use that formula, make sure that you get everything over to one side first. Again, leaving d on the wrong side tends to make this thing fall apart. But if you do use that formula, it can be nice because then you only have to pick out the one point, like point Q, the one that's on the line, plug it in, and then just get yourself an answer. But yeah, again, I tend to prefer using the top method, even though it's slightly more work. I usually feel like I actually understood what I did if I used the top equation, where not so much if I used the bottom equation. But once again, I'm rambling a bunch. So let's look at the next problem down. Everyone's favorite quadratic surfaces. So what we'll want to do on this next problem is look at a bunch of equations for quadratic surfaces and identify what sort of shape they're going to have. There are, in the end, I think there's like 7 shapes we'll be responsible for being able to correctly identify. Oh, yep, it is indeed 7. We can see that drop-down menu and count up to 7. Cool. So we're going to take a look at these equations and do our best to figure out what kind of surface they are. So I've got a few sort of tips that I think are helpful for trying to identify these surfaces. And the first, and what I think is the most important tip, is to ignore every single number that's in the problem. And it's hard to stress that enough, but the numbers in these equations, if all we're trying to do is figure out what kind of a shape it is, the numbers really only complicate things. So I am going to ignore every single number that's in the problem. I'm going to pretend that's not there, not there, not there, not there. I want to ignore all of those because they're just not going to be helpful. In the end, all those numbers are going to do is just stretch our shape in some particular direction. Or maybe it'll shift it up or down by some extra value if we're adding a number in. But it's not all that helpful for just identifying what the shape looks like. So I'm just going to ignore every number that's in these problems. And by ignore, I mean, I'm going to think of every single number as either a 1, a -1, or a 0. All positive numbers, I'm just going to pretend are 1. All negative numbers, I'm going to pretend are -1. And any number that's not present will just be a 0. So that's my first step. Is just pretending all my numbers are 1, -1, or 0. Then I want to try to organize my thoughts in some kind of way to be able to identify what these shapes look like. So I think I've got a cheat sheet down here I've got one at the bottom, and then I've got one from the notes over to the right. Let's start with the one that's in the notes. So first off, I grabbed a page out of the textbook It happens to be on page 854, that talks about what those surfaces look like. And I think it's a decent page to look at because it does give us an actual diagram for each of the shapes that we're trying to identify. But I think that the equations they have written out, there's just a lot going on, and there's some extra stuff there that I don't really need to look at if I'm just trying to identify what the shape is going to be. So I rewrote it to be my own in a way that I think helps make things a little more simplified. So our 7 types of shapes, I'm going to organize into 4 categories. And I'll start with the easiest 3 are at the top. So step 1, any equation in 3 space that can be any quadratic equation, meaning, yeah, let me back up. So we're looking at quadratic surfaces, which means we're only going to be allowing 3-dimensional quadratic equations in order to describe these surfaces. Meaning that the only powers that we're allowing for our variables are 0, 1, or 2. So we'll either look at linear terms or quadratic terms. So we won't be looking at anything beyond, x, y, or z, or x squared, y squared, or z squared. Additionally, all of the mixed variable terms, x, y, y, z, and zx, which do have a place in quadratic equations because they still have a degree of 2, each of those mixed variable terms are only going to rotate our shape. And since we're just trying to identify the very basic shape, like the standard form for each shape, we're going to ignore rotations. So we won't look at any mixed variable terms. We only have those 6 that we just talked about, x, y, and z, and x squared, y squared, and z squared. Okay, quadratic surfaces. They have a quadratic equation. So the first and I think easiest equation to identify is a cylinder, because in 3 space, any quadratic equation that can be written with only 2 of the 3 variables is going to be a cylinder. It means that we're going to define some shape. And the first example would be we're going to define a shape in the xy plane, happens to be a circle. And then the z direction is sort of a free variable, meaning z could be anything and we'll still have the same equation, x squared plus y squared equals 1. So the cross section of that shape does not change at all as I move up or down the z-axis, which is what makes it a cylinder. So again, just by the equation, a cylinder is only going to contain 2 of the 3 variables. Any equation that does that is going to be a cylinder, unless every single term is linear, in which case we're looking at a plane. That's one other caveat we should add. If all 3 of our terms are linear, meaning there are no second powers in our equation, we're just looking at a plane. But as soon as we start adding square terms, we are going to look at some more advanced shape. So first one is a cylinder. It's just taking a 2D shape and adding a 3rd axis to it and not changing that shape at all. The next one is the ellipsoid class, the most famous ellipsoid just being a sphere. And in fact, as long as I'm ignoring all of the numbers, then every ellipsoid is going to be a sphere, which is really kind of the reverse most of the time. All spheres are ellipsoids, but again, it's easier to just ignore the numbers. So when I see an ellipsoid, I'm really going to think of a sphere. I could just stretch or deform that sphere in some way in order to get the actual ellipsoid I'm trying to find. But cool. A sphere is the next equation down. And that looks like the equation of a circle, which remember that a circle, x squared plus y squared equals r squared. A sphere just adds in a z squared term on top of that. So all 3 of our square terms, x squared, y squared, and z squared, all have the same sign when we make a sphere or an ellipsoid. The next category brings us into the paraboloids. And this one is also, I think, fairly easy to identify because it's the only quadratic surface that we're going to look at that contains a linear term, meaning one of our 3 variables has a power of 1 instead of a power of 2. So think like y equals x squared. I have y, which is a linear term, equal to x squared, which is a quadratic term, and that's our base equation for a parabola. So in 3-space, all of our paraboloids are also going to contain a linear term. So if it's got a linear term, it's a paraboloid, and if it doesn't have a linear term, it'll be something else. So for just quick identification, if you see a linear term, it's going to be a paraboloid. From there, we just have two options for the styles of paraboloids that we'll look at. We can either have an elliptical paraboloid or a hyperbolic paraboloid, and that'll be based on the other two square terms. So back to our just 2-space, our two variable equations. We know that we have a circle if we have something like x squared plus y squared, usually denotes a circle, whereas a hyperbolic shape looks like x squared minus y squared. So anytime we've got two square terms that have the same sign, we're going to be looking at an elliptic shape, something like a circle. Whereas when we have two square terms with opposite signs, we're looking at a hyperbolic shape of some sort. So that's the way that I generally remember which one's elliptic and which one's hyperbolic, is I just put it in terms of, okay, did the square terms have the same sign or did the square terms have opposite signs? Same sign looks like a circle, opposite signs looks hyperbolic. Then the tough category are the hyperboloids of 1 or 2 sheets, and then also I'm going to throw the cone in there. Because really it helps to think of these 3 shapes all together. So I'm going to organize my equation, at least in this way. I've got it organized so that all of my variables are over on one side. And I'll set it up so that 2 of them are positive and 1's negative. And if I just focus for a moment on the 2 terms that share the same sign, it's like x squared plus y squared. So let's just ignore the z squared for a moment and look at what it's equal to on the other side. So x squared plus y squared should hopefully remind us of a circle because we've got 2 square terms being added together. And adding those 2 up, again, should look like a circle. If it's equal to a positive number, that's good. I could figure out what my radius is. I've got some sort of a circle that should be in the middle there. But if I look at my x squared plus y squared and I get a negative number, I'm going to have some section of my surface that's not going to exist. I'm going to have some error that's going to come up. So if x squared plus y squared is equal to -1, I've got a circle with an imaginary radius, which means there's part of the graph where the surface just won't exist. And that's the way that I internalize thinking about 1 sheet versus 2 sheets for our hyperboloids. If I've got x squared plus y squared equal to a negative number, there's a section where the surface won't exist, so my 2 sheets are going to have to be separated. My hyperboloid is going to have to be this hyperboloid of 2 sheets that we're seeing over here to the left. Again, that's where x squared plus y squared gets added up and is equal to a negative number. Whereas if it's a positive number, it's going to be 1 sheet because they'll stay connected. Then a cone fits exactly in the middle of a hyperboloid of 1 and 2 sheets because we get our x squared plus y squared comes together to form a single point. And that's in the middle case where it's equal to 0 on the other side. Cool. So that's my whole long-winded explanation on how I go about trying to identify each of these shapes, or how I organize the equations in my head. Let's bring that back over to the problem that we're attempting to solve. We've got 6 equations. We want to figure out which of these equations are what type of shape. So looking through my collection, I don't see any linear terms, which means none of these options here are going to be paraboloids. So I don't need to worry about the two styles of paraboloids. Nothing here is linear. Up now, from there, let's just go line by line. That first one through x squared plus c squared equals 1 plus y squared. Let's see, I have one term, y squared, which has an opposite sign from x squared and z squared. It's because it's over on the other side. If I were to bring that thing around, x squared plus z squared minus y squared equals 1. I've got my one negative term, and it's equal to a positive number on the other side. That thing's got to be a hyperboloid of one sheet. Running out of space. Hyperboloid. Let's just call it hyper of one sheet. Since when I organized all my thoughts, I organized everything onto one side, I was equal to a positive number over on the right. Next up, x squared plus y squared equals 1 minus z squared. Well, if I just bring the z squared back over to the other side, I have all three terms as positive, x squared plus y squared plus z squared. So that one's an ellipsoid. If all three square terms have the same sign, we're looking at an ellipsoid. Next on the list, x squared equals y squared plus z squared. Notice that there's no constant term in that third one. And if I don't have a constant term, I'm looking at a cone. Or rather, if my constant term is 0, I'm looking at a cone. Assuming, again, that I don't have a paraboloid, which we didn't have any of because we know we had no linear terms. Next down the list, we should probably take a closer look at that fourth equation. Let's move that guy up there. Taking a closer look at this guy, I want to reorganize some of my thoughts, or reorganize that equation. I'll look at x squared equals, well, let's go with the explanation I just went with. I want to get as many positive terms as I can. I'm going to multiply everything by -1, giving me negative x squared plus y squared plus z squared equals -1 on the other side. So now I'm organizing it so that I've got some circular looking equation on one of my sides. In this case, that circular equation is y squared plus z squared. And then that part is equal to -1. If I have a circular equation equal to a negative number, I know that I'm going to have that gap in the middle of my surface, which must mean I have a hyperboloid of 2 sheets. So hyperboloid of 2 sheets. Cool. Then after that, the next equation is just the unit sphere, x squared plus y squared plus z squared equals 1. That one's not too bad. And lastly, that fourth equation, another one where I've got no constant term. So we're looking at the equation of a cone. Yeah, fun. So that's our explanation of quadratic surfaces. Another way to potentially think about the paraboloids, the hyperboloids, and the cones, I've got down here. This one instead organizes it so that all terms are positive, or at least as many terms are positive as we can get. So if we take our hyperboloid equations and instead of putting it so that we have all our variables on one side, organize our equations so that every term is positive, then we can look on the term on the side that contains our constant. And if we've got one variable, we have one sheet. If we've got two variables, we've got two sheets. And just a couple of different approaches for trying to identify what these shapes are based solely on their equations. Paraboloids as well, we'll organize it so that our linear term is over by itself. So if we organize it in that case, in that way, our linear terms on a side by itself, then the other side of the equation should either look like a circle, or a hyperbola, either a circle or a hyperbola. So that's the elliptic versus hyperbolic explanation I've got there. Again, quite a few different ways to try to visualize what these equations look like. There's a couple of methods that I go with. Oh boy. All right, let's look at the new stuff. So this will be on there's a couple of homework sets that are due this Friday. That'll be the last couple things that are on the exam, where we start looking at vector functions and introducing calculus. So looking at derivatives and integrals of vector functions. So I think as long as you remember some, like we aren't doing too complicated of derivatives or integrals right now. So as long as you remember some of the basics from Calc 1, I think that most of the calculus part isn't too bad. So we're going to start with this initial value problem. We know our derivative vector, and we know some point that's on our original vector. We just need to figure out what that original vector is. So I'll take the new vector that I want to solve for, regular r of t. It'll be the integral of the derivative vector, where I just have to integrate each piece line by line. So I'm going to integrate the x values. So I have the integral of 10t plus 4. That's our x component. dt. The y component, I need the integral of 5, our y component, dt. And then an integral of the z component, the integral of 12 root t, dt. And see what that thing is equal to. So integrating each piece, this looks like 5t squared plus 4t for the x component, 5t for the y component, and then 8t to the 3 halves for the z component. And just like back in Calc 1, if we're taking an indefinite integral, we should have a plus c that shows up. Only this time around, our c value is a vector rather than just a single number. So there's a plus c for each of the 3 integrals that we did, one for x, one for y, one for z. So we just need to solve for what those c values are, which is where we need the initial value. So r of 1, which is the piece that we got, we know that it's equal to 9, 10, 12. Write that in, 9, 10, and 12. Plus that C vector, C1, C2, C3. Wait, nope. Getting ahead of myself. That is our initial condition. That's the point that is on our vector function R. Now we need to plug that number in to the piece that we have thus far. So plugging 1 in for t, I'll get 5 plus 4. In the first part, I'll get 5 in the y component, and I'll get 8 in the z component. And then I'm adding the c vector into that, to that piece. C1, C2, C3. One for each component. So if I'm looking to get the C values, I can just subtract so my vector at R1 looks like, what is that? 9, 5, 8. I'll just subtract 9, 5, 8 over to the other side and get 0 in the x component. 10 minus 5 is 5. And 12 minus 8 is 4. And that, again, is equal to, just simplify it right down, it's the c vector. So to complete our process, our vector r of t is 5t squared plus 4t plus 0. Then the y component is 5t plus 5 and then our z component is 12, nope, try again, 8t to the 3 halves plus 4. Cool, and that's our new vector function. After that one, parameterizing curves. This is the other fun section. So what we're doing with parameterization is that we're gonna start off by just parameterizing lines, which in 3 space, if we're talking about if we're talking about a curve in 3 space, we are talking about what is essentially a line, but one that might curve around in 3 dimensions. So it won't be just a straight line, but it is still a one-dimensional object that exists in 3-dimensional space. So for a curve, it's just a long, thin line. It doesn't have any width or depth. It's just a line, again, which makes it a one-dimensional object. And we end up often describing that object with 3 variables. But if we're trying to describe a one-dimensional object, we really only need 1 variable to do that. Same with a 2-dimensional object, we only need 2 variables to describe it. If we have a 3-dimensional object, we'll need all 3 variables. But what we're doing with parameterization is taking a curve, which again is just it's a one-dimensional curved line in 3 space, and expressing it using only a single variable. Instead of using x, y, and z, because that's too many variables, I just want to use the minimum number of variables required, or the optimum number of variables required. Again, for a curve, which is a 1D object, I only need the 1 variable. So that's the essence of a parameterization. It's basically just rewriting whatever equation we have to use only the variables we truly need. In this case, 1D object means we only need one variable. So for the first one, the parameterization is done for us. We're given that our curve is 7ti plus 5t minus t squared k. And what? We want to figure out where that thing intersects the paraboloid z equals x squared plus 5y squared. Hopefully after the last problem, we now know that that thing is indeed a paraboloid. All right, let's figure out where that thing is going to intersect. So what we're going to do is set these two things equal to each other, right? If two objects are going to intersect, if a curve and a surface intersect, that means that they should be equal to each other in some way. So I'm going to take the x, y, and z components out of R and plug them into our other equation. So it'll look like this. Note over on our curve, which is R of t, we only have an I and a k component, which means the j component, the y component, is 0. Oh no. Hang on just a moment. Yep, it's fine. This old tablet is struggling to keep writing. There we go. It's back. Okay, so as I was saying, in that R component, in that R curve, we have no J component. So the J piece, the Y piece is 0. So let's take that stuff and plug it into the other equation. So we have an X component is 7t. We have a Z component. It's going to be 5t minus t squared. So I'll just substitute that in. Instead of Z, 5t minus t squared equals, instead of x, I want to write 7t. That thing is squared plus 5, and instead of y, I want 0 squared. So just substituting that stuff in. And now solve that equation for t. On the left, nothing really to simplify. I'll just drop the parentheses. 5t minus t squared is equal to, on the other side, 7t squared is 49t squared. Solve that thing out for t means I want to get all my t's on one side. 50t squared minus 5t. Solving a quadratic equation, I'll factor out what I can. I don't actually need the quadratic formula here because there's no constant term. So factoring will work just as well for us. Plot a 5t, leaving with 10t minus 1. And we'll have a pair of solutions. On the one hand, t equals 0. Or on the other hand, t equals 1/10. From the zero product principle, we just need to set those individual factors equal to 0. Cool. So if we went back to answer the question, because it was in 2 parts, we want to find both the t values where these things intersect and then the actual points. We found 2 t values. They were 0 and 1/10. To get the actual points, all we need to do is plug those numbers in. Probably makes the most sense to plug them into R, or at least it'll be the simplest to plug them into R. So I need R of 0, which I should rewrite what the equation is so I can see it on screen while I'm writing it down. R of t is the vector. Bring it all the way back up here. 7t, 0, 5t minus t squared. Bring that down. Okay, so I just have to plug 0 in for t, which on the first guy, and this is actually a point now, not a vector, 0, 0, 0. So that one was easy. On the other side, I also need R of 1/10. Which looks like 7/10, 0, and 5/10 minus 1/100, or 49/100. Oh yeah, those would be our 2 points. All right, so that's working with a parameterization. Let's look at an example where we have to actually find a parameterization. And we're going to go at it a couple of ways. So I have 2 surfaces. One is a cylinder, one is just a surface. Looks like it's maybe a parabolic surface of some kind, but we don't super need to identify exactly what the surface looks like. I just want to parameterize their intersection. So if I look at the intersection of a couple of surfaces, these are thin 2-dimensional surfaces, but they're probably curved through 3 space. But if I look at their intersection, it should be a curve of some kind. In fact, it tells us it's a curve, meaning we're looking at a one-dimensional, some kind of one-dimensional intersection here. It's a curved line, and I want a parameterization of it. So again, I'm looking for an intersection, which means I want ultimately to be able to set these things equal to each other. And there are a few methods that we'll go about for trying to determine our parameterizations. It all depends on the types of surfaces we're working with. In this example, where we've got x squared plus y squared equals 81, specifically it's equal to a constant on the other side. We probably want to use a parameterization that uses sine and cosine. Since the easiest way to describe a circle is with sine and cosine. So for parameterizing something that looks like a circle, we'll want to use sine and cosine. That's the easiest way, at least, to parameterize our curves. If we had something slightly different, something like x squared plus y squared equals 81z, so a slight alteration to our equation. But if we instead looked at, something other than a constant number on the other side, don't really like the way that came out, we probably are going to want something else, something that's not sine and cosine. So I'm going to make the note, probably something else. How the heck do you know what? Probably something else. Been at it too long, I forgot how to spell probably. So let's simplify it. So again, if it looks like a circle, again, in the circle equation, x squared plus y squared equals a constant, sine and cosine is probably going to be the parameterization to go with. If it's something similar but not exactly that, so if I'll throw in an extra variable on the other side, probably I'm going to go with a different parameterization. And we'll look at an example of that next. So we've got our starting point. It's a circle. So let's use x equal to the cosine component, and our circle has a radius of 9. So we're going to go with 9 cosine. So x is going to be 9 cosine t, which leaves y to be 9 sine t. And again, I'm pulling that 9 just from the fact that I have a radius of 9. It's equal to 81. Square root of 81 is 9. So if those are my two pieces, then I'm after, okay, back that up. I've now parameterized x and y with t. So I've got my x of t, I've got my y of t. I just need to get my z piece. But once I have x and y, I can just plug those parameterizations into the other equation to figure out what z is. Because again, I am looking for a parameterization of their intersection, which means I want to be able to set these two things equal to each other. I started by simply parameterizing the cylinder using sine and cosine, and then I'm going to set them equal to each other to get the parameterization of the curve of intersection. So z we know is 2xy. So 2 times 9 cosine t times 9 sine t. And Bob's your uncle. That's our parameterization. Each of x, y, and z are all expressed as an equation that only contains t. So we can rewrite our entire curve of intersection using only a single parameter t. Because again, our curve of intersection is just a one-dimensional curved line that exists somewhere in 3 space. So it's great when these parameterizations go smoothly, but what happens if they don't go smooth? Let's explore that next. So as an aside equation, I want to find parametric equations of the curve given by the intersection of the two surfaces given here. First one's a paraboloid, and the second one is a parabolic cylinder. So in this one, I see the sum of two square terms. I've got an x squared plus z squared. Ignore the 13 and the 4 for a minute, because usually ignoring the numbers is helpful at the beginning. So I've got a sum of two square numbers, but it's equal to y on the other side, rather than being equal to a constant on the other side, which means that a trigonometric parameterization isn't going to be as ideal here, because we don't exactly have a circle that we're trying to set this thing equal to. So like the radius of the sort of circle that we see show up is a variable. And that's not the best for a trigonometric parameterization. We'd rather not have a variable radius. We like to have a fixed radius when we're doing sine and cosine. So instead, let's scrap the sine and cosine idea and just try, as simplest parameterization, let's try just setting one variable equal to t and see if that works out. So, and again, I want to go through my process here. So I'll say, let's try x equals t. So that's going to be my first attempt. Trying x equals t. From there, I want to solve the other variables in as simple a case as I can. So I'm going to start with the bottom equation because it's only got two variables in it. I've already defined one of them. So I've got, if x is going to be equal to t, that means that t is equal to z squared. And if I then solve that thing for z, all I need to do is take the square root of both sides. But if I take the square root of a variable, I'm going to get plus or minus the square root of t. And at this point, I think that I've started down the wrong path. I see a plus or a minus show up. That's not a great sign. I'd rather not have a plus or minus show up in my parameterization because I'm hoping to be able to just have, one equation for each of my three variables. In the very first step, I got here that I'm going to need two variables in order to describe z, or two equations in order to describe z. So that's not great. So I think that this parameterization didn't work out so good. So we're going to try something else. Let's try something else. Something else. Okay. I'm going to draw a dividing line on here to represent starting the problem over. So x equals t didn't work so well. So let's just go down the line, try the next variable. Let's try y equal to t. And we've only got one spot where we're going to do that. So the first equation, we get t equals 13x squared plus 4z squared. And already that's not looking great. I've got two variables, both of them are square. I don't really know which one to solve for next. There's no clear path forward. I think that this attempt, maybe I'll come back to it if I try another parameterization and it also doesn't work, but this one right now looks even worse than the last one. I don't really see what to do next. I still have some square variables. I'm going to end up with x squared as a square root of z, t minus z squared. There's a lot to dislike about this parameterization. So we're going to do something else. We aren't even really going to consider this one. Hard pass. So draw a new line and start over. Hey. So if that didn't work, how about the third option, z equals t? Well, if we go that way with it, then our first equation, or rather the second equation, but the simpler of the two, we know that x is equal to z squared. But if z is t, that means that x is t squared. And that's not bad at all. There's no square root that we have to deal with there. We already have x parameterized as well. So cool, let's keep working. I can then plug into the other equation, y, which is 13x squared plus 4z squared, will become 13t to the fourth, since x is t squared squared is t to the fourth, plus 4z squared, which will look like 4t squared. And just like that, we have each of our three variables parameterized. So that third substitution, z being equal to t, ended up being pretty easy, whereas the other two looked very much not easy. So in the end, the best looking parameterization that we found easily looks like this. X is t squared, y is 13t to the fourth plus 4t squared, and z is t. So when trying to parameterize some function, when parameterizing some curve, it'll often depend on the specific, what am I saying here? When trying to figure out the best parameterization, oftentimes the start that we have determines how well our parameterization does. So when we tried a couple of parameterizations at the beginning, they weren't great. So we kept going until we found one that was easy. And so if I were to have looked back up at the beginning to decide what parameterization I think might be best, well, I've got two equations that are x equals something and y equals something, right? So I could have a pretty easy equation for both x and y, as long as I already knew what z was. So since I already have two equations that are written x equals something and y equals something, probably parameterizing one of those variables first is not the way forward, because I can parameterize something else first and then come back to x and y. So starting with z would have made the most sense. And indeed, we saw that when we looked at our three options. All right, and then I think I've got maybe just one more problem to do. So let's take a look at our next option. We've got some stuff. We've got a curve, and we want to find its arc length, or rather, the length of the curve. But we're breaking things down into an arc length. So this one's just a bit of plug and chug with some calculus tossed in. We have an equation for the length of a curve, or arc length. And it looks like this. We need the integral from a to b of the magnitude of the derivative vector times dt. And all we have to do is just plug some stuff in and integrate. So let's get at it. I'm going to need a derivative vector. So r prime should look like 2. Then 2 cosine 2t. And then the derivative of cosine, which is negative 2 sine of 2t. Don't forget the chain rule, which is why those 2's come out of the sine and cosine. Right, so there's our derivative vector. We need the values to go between. Looks like t is in between -1 and 4. Okay, so -1 up to 4. And I need a magnitude of that derivative vector, which means I'm going to be looking at the square root of the sum of each individual piece squared. So I'll have 2 squared plus 2 cosine of 2t squared plus -2 sine of 2t squared. All of that's underneath a square root, and then dt at the end. So let's clean up that inside. Integral from -1 to 4. I've got 4 plus 4 cosine squared of 2t plus 4 sine squared of 2t, and then dt. And let's take a quick moment to highlight something that came about. So close. There we go. So within that function, I've got a 4 cosine squared plus 4 sine squared, which is a Pythagorean identity. So one thing to maybe point out over here, sine squared of theta plus cosine squared of theta is equal to 1. So an old identity that'll be helpful from trigonometry, where that thing's always going to hold true as long as it's the same angle being plugged into both sine squared and cosine squared, which is the case here. That's both of those are 2t. Really, the thing is just that expression there is the radius of a circle. In this particular case, the radius of our circle is 2, or I guess, it's equal to the radius squared, but the radius is the important part in there. So I'm going to simplify the inside of that square root, which is nice because trying to integrate the square root of some square trig functions sounds like a chore. And I don't want to do that. So I can draw a better integral sign than that. The integral from -1 to 4, the square root of 4 plus 4 times 1 dt. And all of a sudden that became a much simpler problem. I am just looking at the integral of, well, let's see. I'm going to get the integral of t times the square root of 8 from -1 to 4, which is 5. square root 8. And if we wanted to simplify that even a bit more, call it 10 square root 2. But I don't really think the last step is particularly necessary. 5 square root 8, or at that point, we could plug it into a calculator to find a decimal approximation. Cool, so that's arc length. Then I think I've got a couple more examples that are already done out. I just want to talk about some higher level thoughts without going through all of the work on them. So a few other things that I picked out that I thought might be worth talking about here at the end of the review. Calculating a unit tangent vector. So we've got some function r of t. It's a vector valued function, and I want to find its unit tangent vector at any point. So if I think about what I know about tangent values, that's going to be a derivative somewhere, right? Slopes of tangent lines and derivatives have always been tied together. So if we're looking for a unit tangent vector, first thing I'm thinking of is, okay, I'm going to want a derivative here. So indeed, that'll be the first step, calculate a derivative, but that's not the thing I want to focus on. If I want to get the unit tangent vector, I'll start by getting the derivative. Then I can find the value of the derivative at the point in question, right? We're looking for the unit tangent vector at 2 pi. So I can plug in 2 pi to the derivative function and get a value, or a vector value there. I'll get the magnitude of that vector at the point that I wanted to find it at. And then to get the unit tangent vector, just divide the tangent vector that I calculated by the magnitude of that vector. So the blue line divided by the green line. That part's just the concept that I wanted to get at. Right, unit tangent vector just means get a derivative, find that tangent vector, and then divide by the magnitude. One that a quiz question that ended up being more challenging than I wanted it to. So I want to talk about it here. If I'm going to take some vector A and project it onto I, which is the unit vector in the x direction, that means I only want the x component of that vector, right? So the projection of A onto I is 3 in this case. If I wanted the projection of A onto J, it'd be 13. Projection of A onto K would be -2. Those were supposed to, but I was hoping that question went easier than it did. So in these quizzes that we see on D2L, anytime you see a bold I, J, or K, they're referring to the unit vectors in the X, Y, and Z directions. And usually when they show up, they're just there to be a simplified version of the problem. So those are meant to be easy. Yeah. So same thing with this next one down. We're calculating a cross product, and then we're going to take the dot product of that cross product with J. All that really means is take the cross product, and then the answer that you're going to give is just the J vector. So the reason why some of these questions are written this way is that entering a vector value into D2L is complicated, because D2L is not quite sophisticated enough to recognize that a vector is a thing. So instead, we're just going to say calculate the cross product, but then I only want one of the 3 values in the cross product. So in this case, I want the Y component. So if I take, A cross B dotted with J, that means just take the Y value of the cross product. If we dot it with K instead, that just means enter the Z coordinate of the cross product. If dotted with I, take the X component, like we saw previously. And then here's a whole fun other problem. Getting the line of intersection between a couple of planes. There's a whole lot of work that goes into solving it, which I've already done ahead of time. I just want to talk about the process that I'd use for getting through that. So if I want an intersection of two planes, I know that I'm looking for a line that exists in both planes, which means that the line of intersection has to be perpendicular to both normal vectors, because all lines within a plane are going to be perpendicular to a normal vector because that's what the normal vector is. So if I know two vectors that I need my line to be perpendicular to, I can take their cross product to get a tangent vector to that line, or a parallel vector for that line. So for an intersection between planes, a cross product of their normal vectors will get me a parallel vector. Then once I have the parallel vector, I just need any point that is on that line, which is this first bit of work. And I can take any point that's on that line, which means the choice of the point that I use here is going to be completely arbitrary. In this example, I just set z equal to 0 and solved for x and y by using the two equations of planes. But really, I've got two equations with three variables, which means I'm overdetermined. So just pick one of your variables to be any number you want. Usually 0 is one of the easiest numbers to do that for, but sometimes 1 is slightly easier. But again, totally a free choice. Pick anything you want, because all we need is any point that's on the line. So that's the first bit of work that we did, or first bit of work that I did. And then once I've got my equation of the line, I want to find the angle between the two planes. And it's helpful to rely on the definition of dot product to find that angle. So the dot product of the two normal vectors, I can find an angle between those two normal vectors, and then say the angle between the planes is the same as the angle between the normal vectors. So that's the second half of the problem. And then one more example with some parameterizations. This one I thought was just a tricky web work problem, so I thought I'd throw it here on the review as well. Because really, if you can understand what's going on in this web work problem, I think you're going to be all set for the parameterizations that are on the exam, or the working with parameterizations on the exam. You'll still need to make sure you can come up with a parameterization on your own. But we've got these two curves, figuring out where they intersect and the angle at which they intersect. Well, I just want to set the curves equal to each other. So I'm going to set each of their components equal. So the x components, the y components, and the z components. And then I have a system of three equations with two unknowns. So I just need to check through a couple of them and see that I can find a solution. So with my three equations that I now have, one for x, one for y, one for z, I'm going to solve the simplest one first, which, looking across those three equations, I said that z looked simplest. So I solved there first, and then I'm going to plug that solution into the next simplest. So I solved for s, got it was -2 minus t, plugged it into the next simplest equation, which looked like it was y, got an actual value for t. Plug it back into the first equation to solve for the other variable. In this case, I got that s was -3, and then plug both of those numbers into the third option, into the third equation, just to check that they do indeed intersect. Because once we plug that in, we should get the same number on both sides when we plug in for both t and s. And if we do not, that means one of two things. Either there was an error when calculating our numbers, or more conceptually, if that third equation doesn't line up, like if I don't get the same thing on both sides, that means that these two curves do not intersect. So if I plug in my two numbers to the third equation and don't get something true, then the curves don't intersect. But then for finding the angle between those two curves at their point of intersection, pretty similar to the one we did with the planes, I need to find this time I'm going to take their tangent vectors or their parallel vectors instead of the normal vectors, but same idea is going to apply. If I know the angle between their tangent vectors, then I know the angle between the two lines at their point of intersection. So I'll use the same idea, going back to the definition of dot product, because it's got cosine of theta in there. Oh man, I even had one more. Right. So this one was just a bit of a trickier example for calculating arc length. So the one that we went over, we were lucky that our integrand came out to just a constant number. The integral was particularly easy, but this one works out to be slightly less so. Our inside doesn't work out super nice in the way that our last one did. So we're going to need a u substitution in order to solve the thing. And so I ended up factoring out any square numbers that I could, set up a u substitution, and solved it out that way. I know that this review's already gone on for quite a while, so I didn't want to cover the whole thing, but it seemed nice to, have an example of a u substitution integral on here in case you wanted to review that for the exam.